Hi everyone, so this is a review for Chapter 14 Revision Quiz, Set 2. So based on the responses received below, we'll be discussing question 2, question 4, question 7, question 12, 13, 14, and 15, a total of 7 questions. So let's look at the first question. Question 2. The diagram below shows the change in pressure and volume of an ideal gas through two paths, PQR and PSR. So there are two paths available. One is going up and then going to the right. We call this PQR. And there's another one which is PSR, which is going to the right first, then going upwards. For the change through the path PQR, the heat absorbed by the gas is 32 joule. So we can say from the process of PQR, the heat absorbed, which is heat flowing into the system, is 32 joule. So it should be a positive value. So next, what they're asking is, what is the heat absorbed by the gas or the change for the change through the path PSR? Okay, so now they're asking for what is Q for PSR. So what can we do? Okay, we will need to do a bit of stuff. Okay, so from this PV graph, we know that from PV graph, we'll be able to get the work done, because work done is just the area under the graph. Okay, this is area under the graph. Okay, then what else do we know? I think that's good enough. Okay, so we know that we'll be able to get work done from the graph, and they already given us the heat through the question. So to relate the work done and the heat together, we'll probably need the first law of thermodynamics. So that would mean by the change in internal energy for PQR should be equals to the heat flowing into the system for process PQR minus the work done by the system throughout the process PQR. So this is what we built based on the process of PQR. So what can we do is we find PQR, Q is given is 32 joule, then minus what is the work done for PQR? Well, it's just the area under the graph for PQR. So this process PQR here, if you want to get the area under the graph, this would be the area under the graph. So if you calculate things, better we calculate it slowly. Calculation will be 5 times 10 to the power of 5 multiplied by 6 minus 1 times 10 to the power of negative 5. So if we multiply these two things together, calculate, let's put a bracket here to be more careful. Okay, then you get 32 minus 25. So doing that, you'll be able to get the answer to be 7 joule. So this is the change in internal energy if you go from P to R through the path Q. But remember one thing, change in internal energy doesn't depend on the path. Okay, delta U is independent of path. Means by no matter what kind of path you use to go from P to R, you get the same delta U, independent of path. Okay, so what that would mean is the change in U for PQR should be the same as the change of U for PSR. Okay, let's slide a bit over. Okay, So these two should have the same change in internal energy because they have the same initial state, they have the same final state. And we say it's independent of path. So if the initial and final states are the same, so the change in internal energy should be the same. Okay, this is a property for internal energy. The change is independent of the path. Okay, so with that said, what can we do now is we can find PSR, which is equals to Q of PSR minus work done throughout the process PSR. We know that this is equals to delta U PQR, and the Q is what we want to find, whereas PSR will be, PSR is this part over here. Remember, area under the graph. So as you can see here, the process PS will get us this green area under the graph. The process of SR over here will not contribute any area under the graph. So therefore, the only area under the graph we have is this rectangle below the PS line. So with that said, we are able to calculate the work done. So it will be 2 times 6 minus 1. Sorry, it shouldn't be 2. It should be 2 times 10 to the power of 5. Always forgot the exponent. 2 times 10 to the power of 5 multiplied by 6 minus 1 multiplied by the exponent times 10 to the power of 5. Okay, so if you calculate all these things, let's write down change of PQR is 7 joule. Q PSR is what we want to find. Then minus. Then you will get 10 over here. So if you move things around, then you get Q of PSR to be 17 joule. That's why the answer for this question will be 17 joule. So to be able to solve this question, you have to be aware of the fact that no matter what path you use to go from the initial state to the final state, your change in internal energy should be the same if the initial and final state are the same. Okay, so it means by, let's say today you want to go using this path over here. Yay! Then you reach here. Okay, so the path you use is a very weird path, but if I ask you what is the internal change in internal energy, you should still tell me that it's 7 joule, because the initial is P, the final is R. So same as these two processes that we have here. Therefore, you should have the same change in internal energy. That's the main concept that they are testing behind this question. Okay, so that's all for this question. Let's move on to the next one. Question 4. The graph above shows the variation of pressure P with volume V. So they are saying that the above graph is a PV graph for 0.04 mole of an diatomic gas. Okay, seems a bit packed, so I'll write outside. So the number of mole is 0.04 mole. And since they say it's a diatomic gas, then you know that the degree of freedom should be 5. Okay, we usually exclude the vibration because we don't really explain things in very, very high temperature. So we usually just exclude the vibrational mode. So the degree of freedom is 5. Then we know that the gas expands adiabatically from state X to state Y. So this is the adiabatic expansion from X to Y, and they ask for the internal energy change in the process XY. So they're asking how much change in internal energy does it is happening here from X to Y. So how are we able to find that? change in internal energy is delta U. Then that will be U final minus U initial. So U final, you have many ways to do that. You can do it like this, F over 2 and R, then you can have delta T here, then delta T will become TF minus TI, then you can use the P, V, and N to find T for initial and final. Okay, basically what you can do is PV equals to nRT, then you have P, you have V, you have N, you have R, then you are able to get T. So if you do it for initial, you do it for final, then you substitute in the change in temperature, you get delta U as well. But here I would like to introduce a shortcut actually. Not really a shortcut. It's a way of rearranging things so that you can do everything in one shot. So the thing is, I can say this is equals to F over 2 nRT final. Then I will say this is minus F over 2 nRT initial. Okay, so once I know that, I can factorize out only some stuff that I want to factorize out. I would like to factorize out only F over 2. Then now what's inside here will be nRT final minus nRT initial. Well, if you look over at this equation over here, you know that I can change it to F over 2 P final V final minus P initial V initial. So with that, with one single block of calculation, I'm able to get the answer. Just require a little bit of arrangement. So it's 5 over 2. Then the pressure should be, for final, the pressure should be 1.1 times 10 to the power of 5 times the volume, 8.0 times 10 to the power of, oops, I'm blocking myself, I can't see the number, times 10 to the power of negative 4. Then minus the initial pressure, that will be 20.2 times 10 to the power of 5, multiplied by the initial volume, which is 1.0 times 10 to the power of negative 4. So if I multiply, minus, I do everything, okay, let me arrange it, let me write it nicer, using square bracket. Okay, so if I calculate everything using calculator, the answer that should come out is negative 285. So with that said, we know our answer should be negative 285. Okay, so with a little bit of wise, if you know how to factorize things that you need outside, that you leave stuff inside, then actually without even knowing the number of moles, you are able to solve the question. See, I'm not using the number of moles given. The only information that I use properly is the diatomic gas information. So you are able to do it also using this way. Okay, so that's all for question 4. Let's move on to the next question. Question 7. The graph shows a fixed mass of ideal gas undergoing changes in pressure and volume. Again, it's a fixed mass. Fixed mass means by the number of moles should be the same. The number of moles should be constant. Then, ideal gas undergoing changes in pressure and volume. Basically, they're telling you that this is a PV graph. What is the net work done by the gas for its states change from L to K to J to L? So it means by if the gas undergo thermodynamic process going from here to here, then to here, then to here, what would be the net work done? Okay, so there are many ways of doing it. I'll show you one of the way probably. So the work done for this cyclic process, we call this cyclic because it goes back to the initial state. So it will be LKJL. So that will be equals to, you add up all the work done throughout the process. So you have work done for part LK, and you have work done for KJ, and you have work done for JL. So split into 3 sections. So now we can do it slowly. For the part LK, you see that there's no area under the graph. And as I say, area under the graph is just the work done by the gas. Okay, so LK, these processes does not contribute to any area under the graph, so it will be 0. Whereas for the process KJ over here, you see that the area under the graph would be this rectangle over here. Okay, so you can calculate it. Of course, you can calculate it to be 1 times 10 to the power of 5 multiplied by 5 minus 3 times 10 to the power of negative 3. Okay, so you can square bracket these things up. And these are all under work done by this process KJ. How about process JL? How much area do you have? So for this process JL, you have to be a bit careful. Yes, even though the area under the graph, you can identify it to be this portion over here. But the issue with this process JL is that it's going to the left hand side. If you see the arrow is going towards the left hand side. So if you this is related to integration, but if you reverse the limit of your integration, you will actually change the sign of your answer. Okay, that's the same situation here. If you calculate your area from left to right, then it will be positive. But now you are getting your area from right to left. So right to left means by the answer will actually be negative. So this is actually a negative area. So what I can write here is, I can write I'll just write negative here first, then without making it complicated, just write negative. Then to calculate this, I can use the idea of a trapezium. Okay, trapezium is half then A plus B. So my A will be here, my B will be there. Okay, so A plus B is just 6 plus 1 times 10 to the power of 5. Okay, then you multiply it with h. The last step is h. h is 5 minus 3 times 10 to the power of negative 3. Have to be a bit careful with all the brackets and stuff. Yes. Then if you calculate the answer, I believe the answer that you get should be negative 500 joule. Okay, but things doesn't really have to be that complicated. If you can observe the graph graphically, let me remove everything. If I rewrite this equation, work done LJKL equals to work done for process LK plus work done for process KJ plus work done for process JL. You see that process LK over here will contribute 0 work done. Work done by KJ over here, you see that it contributes to a rectangle. Whereas for JL, you contribute this trapezium over here. But be a bit more careful is, because this is going from right to left, therefore it's not positive, it should be negative. So if you notice carefully, if I take the difference between this rectangle and this trapezium over here, what I should end up with is just a negative of the triangle up there. Okay, so if you are doing this fast, I mean this is an objective question, right? You can just do WLJKL equals to half times height times width. Height is 6 minus 1 times 10 to a power of 5. Okay, then you multiply it by the width, which is 5 minus 3 times 10 to a power of negative 3. So if you calculate all these things, oh, remember there's a negative sign, bring this negative sign here, you end up with negative 500 joule as well. So this is a much faster way of getting it. You just need to know there's this much positive and that much negative. So the answer should be the difference with a negative sign. Okay, so with that we calculate our answer to be negative 500 joule. They are asking for work done by the gas. Yes, what we are calculating here is work done by the gas. So if you get our answer to be negative 500 joule, means by technically what happened is there's 500 joule being done on the gas. Okay, so if you're calculating work done by the gas, you get positive value. That means work done is indeed by the gas. But if you get negative value, that means work done is actually not by the gas. If you get negative, it means it's not by the gas, it's on the gas instead. So I can say negative 500 joule of work is done by the gas is equivalent to 500 joule of work is done on the gas. Here I repeat, negative 500 joule of work is done by the gas is equivalent to 500 joule of work is done on the gas. If you switch the by to on, then you can change the sign, okay, because they are opposite things. Okay, so that's it for question 7. Let's move on to the next question. Question 12. The air in an aircraft in flight has 12 megajoule of kinetic energy as a result of the motion of the aircraft. Okay, well, this is a bit advanced. Now you enter aircraft. So I'm so sorry for my poor drawing, but this looks like a chicken wing more than an aircraft. Okay, this is your aircraft. Inside your aircraft there's air. Now it doesn't even look like a chicken wing. Not chicken wing, drumstick. Okay, so this is an aircraft. Inside aircraft there's air. So because now they are saying because of the motion of this aircraft over here, you have 12 megajoule of kinetic energy. Then at the same time, because your particles are moving randomly, okay, let me just draw this randomly. Okay, because of the random particle of motion, you get 35 megajoule of kinetic energy. At the same time, because you are this far from the ground, you get gravitational potential energy. That's normal. You have 80 megajoule of gravitational potential energy because you are at a certain position, at a certain height away from the Earth. Okay, then at the same time you have negative 5 megajoule because you have intermolecular attraction between the air molecules. It means by this molecule is slightly attracted towards here, this molecule is slightly attracted towards here, this molecule is attracted towards here, this molecule is attracted towards here. Yes, there's attraction between molecules in real life. Okay, so they're asking what is the internal energy of air in the aircraft. Well, okay, this is something a bit new. This is a fresh question. So if it's asking about internal energy, you have to be aware that internal energy is the sum of kinetic energy of all the constituent particles and the sum of potential energy due to the attraction between the constituent particles. It means by we only care about the particles. We only care about the stuff inside the system. We don't care about the system itself moving. The system moving, those things we consider it external. Okay, it's not related to internal energy. Internal energy cares about the particles in the system, and it cares about the attraction between the particles in the system. They don't care what kind of influence is happening outside, because those it's external to the system. So if that's it, we can say the motion of the aircraft is an external thing. It's the system itself moving. It's not the gas particles inside the system. Okay, it's the system itself moving. So it's not related to internal energy. Random movement of air molecules, yes, that's the particles in the system. The altitude of the aircraft, that is the system itself being positioned at a height. Okay, it's regarding the interaction of the position and the interaction between the system and the environment. So it's something external, so it's not related. Then you have intermolecular attraction, which is the attraction between constituent particles. This is correct as well. So what is the internal energy? Basically, you just sum up all the kinetic energy for the constituent particles and you sum up all the potential energy for the attraction between particles. Then if you take 35, you sum up with -5, then you end up with an answer of 30 megajoule. That's why your answer should be C, 30 megajoule. So I hope this one can help you to be clear what is internal, what is external. Remember, it's only related to the particles inside the system. We don't care about its interaction of the system with the surrounding. Okay, so this is question 12. Let's move on to the next question. Question 13. The figure shows a gas sealed in a cylinder by a weightless and frictionless piston. So this piston here is movable and it's weightless and frictionless. Okay, now later I'll explain why they purposely write weightless and frictionless. So the gas at 5200 Pascal is slowly heated until the piston is pushed up by 3 cm. So at the end, we'll probably see that this piston has moved up a distance of 3 cm. So what they ask is, what is the work done by the gas? Okay, they're asking for the work done by the gas. Okay, so let me go through the question just now. Why do they purposely write the word weightless? And why do they purposely write the word frictionless? Okay, why they write weightless is, if you look at the free body diagram of the piston, FBD of piston, what you will see is, this is the piston itself. The pistons will experience a push upwards due to the what you call it, pressure, not forced by the air in the system. At the same time, because there's air particles outside, the atmosphere will also push it downwards. Okay, it's just that we usually divide it by the cross-sectional area to make it become pressure. Okay, so usually if the pressure inside and the pressure outside, they are equal, then this piston will not be moving. And this is only true if this piston here is weightless. Okay, because if this piston is not weightless, what will happen is you have another force, which is the weight of the piston itself. So if that's the case, right, if you want the piston to be not moving, you need to have greater F air in the system. If the piston has weight, then F air in system must be minus F system must be equals to the weight of the piston. So that means by our F air in system, not fair in system, F air in system must be greater than the F of the, not system, why am I writing system? F air of the atmosphere. Down here is also F air of atmosphere. equals to the weight of piston. So it means by you need to have greater pressure inside the greater gas pressure inside the system in order for the piston to be not moving. That's the case if you have weight. Means by the pressure inside need to be greater than the pressure outside, only the piston will not be moving. Because you need to have greater pressure inside to balance the weight of the piston, at the same time balance the air pressure of the atmosphere. So there are two things pushing down and one thing pushing up. So this one thing pushing up, you have to have greater magnitude compared to this F atmosphere. That's why inside pressure must be greater than outside pressure to make the piston not moving. So that's the case if the piston has weight. But now they tell you that this piston is weightless. So it means by you have no weight of piston. So if that's it, then you know that the F air in the system will be equals to the F air of the atmosphere if the piston is not moving. Okay, so this will make the situation a lot easier to be analyzed. Okay, the second thing is why is it frictionless is to prevent energy loss. Okay, we say heat flow in, heat flow out, work done by the gas, work done on the gas, they are all, if you sum them up together, they equals to the change in internal energy, right? But if you happen to have friction, it means by you need to use up more energy to move the piston because some energy has to be lost through friction. So it means by your delta U equals to Q minus W. If you need greater work because you want to overcome friction, it will make this thing not equal anymore. Okay, because you need greater amount of energy, you need greater amount of change of energy to cause this work done that you see. Okay, because some energy will be lost. You just need to know some energy will be lost through friction if it's not frictionless. If some energy is lost, that means by this equation here will be not abide. Okay, it will not equal anymore because some energy will be lost. That's why it must be frictionless. Okay, so now they ask what is the work done by the gas. So work done by the gas, there are many formulas to calculate work done by the gas. But if you see here, they specify the pressure to be 5200 Pascal. I think the question, the one that makes the question is leading us to believe that this is an isobaric expansion. So it means by the pressure is kept constant. So the pressure is kept constant means by when we solve this question, we can find the work done by the gas by just using P V final minus V initial. So the pressure is 5200 and the change in volume, we can do it this way. You can find a cross-sectional area times the change in height. What do you usually call change in height? Let's call it D then. Okay, so 5200, then the cross-sectional area is 0.40, then the change in height is 3 cm, that will be 0.03. So if you multiply everything together, you should get, what answer should you get? But they are not calculated. 5200 times 0.40 times 0.03. The answer should be 62.4 joule. Okay, so if that's it, you know our answer should be 62.4 joule. Okay, why is it positive? Why is it not negative? Because they are asking for by, and this thing that we are calculating here is indeed by the gas. Okay, if you do your calculation here and the answer appears to be negative, if the answer here appears to be negative, then your work done by the gas will be negative. Okay, if they ask for what is the work done on the gas, if they are asking what is the work done on the gas, and you get the answer of negative 62.4 over here, negative 62.4 that you calculate over here is by gas. So if you change it to on gas, it will be 62.4. Then your answer will be 62.4. Just need to know how to convert between them. What you're calculating is always by gas. If you want to change it to on gas, you flip the sign. That's all. Okay, so that's for question 13. Let's move on to question 14. Question 14 says, a mole of an ideal gas is compressed isothermally. Compressed isothermally, so it means by the volume is decreasing, then the T is constant. From a volume which is V to another volume which is 3/4 volume at a temperature of 500 K. So they already tell us this isothermal compression is happening at the temperature of 500 K. And now they ask for the work done on the gas. Well, this should be a relatively direct question. For isothermal compression, you know the equation should be work done equals to nRT natural log V2 over V1. V final minus V final over V initial. So 1 mole is the number of mole that they say here. Okay, I miss it, it's here, 1 mole. And this is R, which is 8. Yes, this is the gas constant. The temperature is 500 Kelvin. Then we have natural log. V2, the final is 3/4 V. The initial is V. So you can do a bit of cross out. Then if you do use your calculator to calculate this, the answer that you get is negative 1195.97 joule. Okay, so if you're calculating work done by gas right now and you get negative answer, so if you get negative answer, what will it mean is actually this work done is on the gas. Actually, it's work done on the gas. So now they're asking for work done on the gas, so you can give the positive value because you flip the sign if you change it to on the gas. So it will be positive 1195 joule, positive 1195 joule. So that's it for question 14. Let's move on to question 15. When the volume of a gas changes from 1.6 meter cube to X meter cube at a constant pressure of 12 kilopascal. So this is the initial, this is the final volume. So this is V1, this is V2, then your constant pressure is 12 kilopascal, constant pressure. So now they tell you the amount of work done to the gas. Well, amount of work done to the gas is actually on the gas is 2400. Okay, 2400. So this is work done on the gas. So if it's work done on the gas, when you calculate this, how should you calculate this? Usually when you calculate this, this is work done by the gas. This is by the gas. Now, if you want to flip it to on gas, means by the value that you get for work done here should be flipped. So you should change to negative 2400. And now you can do your substitution. P has a value. The value is 12 kilopascal. So if you calculate all this, you should end up with an answer of 1.4. Okay, therefore your answer should be B, 1.4. You see the work done to the gas, work done on the gas is positive, means by there's work done on the gas. If the work done is done on the gas, then the volume should be decreasing. The volume should be decreasing. So the answer that you get should be smaller than the initial volume, which is 1.6. So our answer should be 1.4 meter cube. Okay, you have to be careful to flip the 2400 joule to negative sign. Because this work here, you substitute, you are supposed to substitute by gas. but what they give you is on gas. So if you want to change on gas to by gas, you have to change this positive value to a negative value. So if you substitute it inside, your answer should be 1.4 meter cube. Okay, so that's it for our... Is there any more question? No. So that's it for our review of chapter 14 revision quiz set 2. Thank you very much.